And then our radius is 0.03. Okay, that is our radius. So this will be equal to 750 times by 0.03 divided by 1.272 power minus 6. It's equal to 17.688. It's equal to 17.689 times 10 to the power 6 Pascal. Okay. So by looking at the direction, so the direction is always also towards the right. Okay. Why towards the right? Because the torque is applying this way, so the shear stress will be going in this direction also. And the direction of the shear stress due to the torque and due to the shear flow are in the same direction. Okay. So now it's time to form our element now. Okay. So let me get this image over here. Right. So we are going to sketch our element out. Okay. So this is our X. This is our Y. And this will be our Z. Okay. So we know that in our stress Y, we have compression. So the normal stress is the easy. The compression is what? 89.128. Okay, 89.128 times 10 to the power 6 Pascal. Okay. By looking at the shear, right, the shear is going to go this direction. Right, the shear will be that direction. And it's equal to 2.358 times 10 to the power 6 plus by 17.789 times 10 to the power 6. So this will be equal to 2.358 plus 17.689, 20.047 times 10 to the power 6 Pascal. Okay. Right, I'm going to do something else to make sure you comprehend better. Now, what if, okay, I'm going to have an element K over here. Okay, we are going to have our element K. I deliberately put our element K over there. Okay, so element K is behind now. Right. So now, how does the shear stress look like now? Okay, it's the shear stress. The normal stress is always the easy part, right? It's the shear stress. So this is our element H. Right. I'm going to put this here, and we're going to do our element K. Right. So element K will look like this. It's on the other side. Right. Yeah, come on, Eugene, draw properly. Come on. Right. We still see the normal stress of what? Of 89.128 times 10 to the power 6 Pascal. Right. But how does the, sorry, this is the, how it will flow, the shear. But how does the shear stress look like? Okay. So due to now, the shear stress due to the shear force is still in this direction. Okay. So this direction, I'll use different color. This direction, right? The shear stress is still due to your shear V. I cannot remember Vx. Is it Vx? Yeah, Vx. But the torque is inducing the opposite direction. So this is your what? This is your Ty, right? Due to your shear, due to your Ty, and then your shear due to your Vx. So the resultant is depending who is bigger, okay? So the shear due to Vx is equal to 2.358, right? And then the shear due to the torsion is 17.689. Okay. So you know that the shear due to the torsion will be higher, right? So now the shear stress will look like this. Will be in this direction. Right? Will be in that direction. And this will be equal to 17.689 minus 2.358. 17.689 minus 2.358 is equal to 15.331 times 10 to the power 6 Pascal. Okay. So for this case, yes. Oh yeah, the moment. Sorry, you're right. Thank you. So this one we need to find out. You're right. Yeah, because when it's compression, you're right. Thank you. So this one we need to find. Sorry, I think you're right. Thank you. 2 pints of beer. Okay, we still don't know what is this. Okay, it's not that we don't know. Okay, let's find out. Okay, so it will be equal to what? Okay, it will be equal to minus 4.245, right? Times 10 to the power 6. Okay, minus 4.245 times 10 to the power 6. And then it's going to cause so now our element is over this side, right? No, not this view. Sorry. In this view, our element is over the other side. So it'll be tensile. So it'll be plus what? Plus 84.83. 84. Thank you for pointing this out to me. Okay. Sometimes I jump ahead. So this is equal to minus 4.245 power 6 plus by 84.883 power 6. It's going to be tensile now. Okay. So this side is going to be tensile. Okay. 80.638 times 10 to the power 6 Pascal. That's why he gets 2 pi. Okay. Right. So that's why I want you all to see not just the shear, the normal shear to say. I'm having trouble picturing how the torque is in the opposite direction. Okay. If you look at the torque, right, at element K, the torque will also be in this direction, EY. Jihan, you see that now? So the direction changes, Jihan, yes? Where it's at H and as K, okay? So as I said, I've not done a torsional problem before, and I kind of like it, okay? So that's the only thing that you have to consider, okay? Right, so that's all I'm going to do with combined loading for now, okay? So the next topic I'm going to teach is going to be on shaft, okay, combined loading of a shaft. So you have torsion, you have gears. I realize that I cannot teach that until I teach you guys 2D and 3D Mohr circle, okay? So let's look at 2D Mohr circle first, okay? Oh, some of you are still copying. Are you all okay? Or So no one. Okay. So let's look at Mohr circle. So before we deal with Mohr circle, I want to elaborate what do we mean by plane stress analysis. Okay, what do we mean by plane stress analysis? So if I were to draw a cube now, okay, I'm gonna sketch a cube. Okay, then I'm gonna draw our transformation x, y, z. Okay, so over here we know that we have our stress x. We know that this is our stress y, and we're also aware that this is our stress z, right? So when we elaborate plane stress analysis, what do we actually mean? Okay, so when plane stress analysis is stress x and stress y, okay, stress x and stress y are not equal to 0, okay, and stress z is equal to 0. So that is what we mean by plane stress. Or it can be stress x and stress z not equal to 0 and stress y is equal to 0. Or it can have stress y and stress z is not equal to 0, where stress x is equal to 0. So any one of these conditions is what we classify as plane stress analysis. Okay. So from here, there are another factor that I want to describe to you. What do we mean by in plane? And what is out of plane? Okay. So I've been trying to read textbook to describe what do we mean by in plane and what do we mean by out of plane, and I cannot get a clear definition. Okay, so I'm going to draw another element for you. That's not necessarily a cube. Okay, so the transformation. This is x, this is y, and this is z. So I'm going to draw an element now. Okay. So we know that this plane over here is our yx plane or xy plane. And then this element over here is our yz plane, or this surface is our yz plane. And the surface over here is your xz plane. However, I'm going to call this in plane. And I'm going to issue this out of plane. And the last one is also out of plane. Okay. Now I'm going to carry on again at 10:30. Okay, I'll see you guys later.